Fitoptivis is a European research project whose objective is to develop a global approach for the intelligent integration of image and video processing in cyber-physical systems. Images play a relevant role in human perception for the full understanding of their context. The same occurs in cyber-physical systems, as they need this visual context for correct decision-making, meaning this is the implementation of a series of specific actions. In order to build this visual context, advanced image and video processing must be performed, requiring to process a large amount of data and obtaining results almost in real time. The main challenge that Fitoptivis addresses is to achieve that visual context for cyber-physical systems through the application of sensors and actuators which, in turn, balance energy consumption and performance, something essential in such critical systems. ITI is providing an innovative three-dimensional industrial inspection technology, zero-gravity 3D, to the project, applying innovative 3D computer vision techniques to capture, reconstruct, and compare images. The challenge for ITI is to improve the efficiency and general performance of the solution for its application in cyber-physical systems. To do this, a new prototype, Mini i3D, is being assembled, implementing an edge architecture that will reduce the network bandwidth usage. In addition to that, new algorithms are being developed, making it possible to manage the edge boards dynamically during the runtime and featuring the change of the pipeline of each board depending on its state and capabilities.
The Mini i3D prototype has been adapted to include an edge computing component which is called edge capturer. Because of this, the system can be divided into two main parts, one being the distributed system and the other the edge component. The edge capturer is the main development carried out during this project. Due to this, the component has been modeled in QRML, a description language developed by the Fitoptivis Consortium. The model defines an application and an execution layer. The hardware is composed of cameras and edge computing boards which are abstracted, making possible to give alternatives in terms of the board type to use. As an example, NVIDIA Jetson Nano or Raspberry Pi boards can be installed to perform edge computing operations. The software layer encapsulates two subcomponents: the image transferring for managing image data transmission and so the bandwidth usage, and the image segmentation which selects different methods depending on the system load. In the distribution side, there is a master computer which communicates with the capturer to request a new image from the cameras. Later on, when the edge boards send the images taken by the cameras, the capturer stores them in a queue where the master is able to read them. The master also includes a workload dispatcher that distributes the captured images among workers, where the reconstruction of the object is finished.
When the prototype is turned on, the power supply feeds all the systems, including the computers, cameras, and edge boards. After this, the system checks the cameras and the flashing lights. Several LEDs are lighted up to show everything is working properly. In addition to this, there is a configuration procedure where the hardware is assembled or a new part has to be inspected. Firstly, it is required to check the arm, the throwing mechanism, so that the pieces will have a trajectory as perpendicular as possible. Later, the alignment of the cameras is carried out, measuring distances from the camera to other components of the system. The next step to perform is the calculation of points where the objects reach the maximum height after they are thrown. That point is where the cameras are focused to take a capture. Once it's done, an additional fine alignment and calibration for the cameras is performed. The object to inspect has to be modeled using a 3D tool. The new model is then introduced in the system, and the geometrical data and other parameters such as tolerance are also registered.
During the operation, there is a graphical user interface to help the user to perform the required actions that rule the device. A pre-configured task has to be selected. It contains all the parameterized data to inspect on an already modeled object. Then it is possible to start and stop this task. When it is running, images are stored in the long-term storage and data is sent to the monitoring system. The monitoring system provides a dashboard to visualize the current status and also makes possible to throw system warnings.
Mini i3D makes use of FIVIS as its monitoring system. FIVIS is a monitoring solution developed by Charles University, another Fitoptivis consortium member. Regarding the information to be gathered, Mini i3D gets data about network bandwidth, throughput, measures as inspected per minute, CPU load and memory usage. To collect all this data, a software agent called Telegraph is installed in all the 16 edge boards, and ITI has created a Telegraph plugin to transform the data into FIVIS input format. The plugin is based on the Telegraph JSON serializer, so it is consistent with the software architecture and provides JSON document with serialized data which is compliant with the required format. This way, the agent in each board sends the information to the Raspberry Pi, which centralizes the data gathering. Then everything is sent from a Raspberry Pi to FIVIS. Additionally, a local monitoring system is also available using an InfluxDB as a storage and chronograph to display dashboards.
A first version of the demonstrator is ready. The prototype is fully assembled, having all the 16 cameras and edge computing boards installed. This hardware follows the reference architecture already represented in QRML. Moreover, the CamEdge software component has been adapted to the new edge architecture. Currently, the device is capable of capturing images and generating the 3D representation of the object. Finally, the prototype has the capability to send data to FIVIS. At the same time, ITI has developed a Telegraph plugin for FIVIS that can be exported to other use cases and Fitoptivis consortium members. The agent and its plugin can be installed on almost any device capable of running Linux, and this way, the device will send the information collected by Telegraph to FIVIS. The complete version of the prototype will add the runtime configuration when the device is started. Additional algorithms for resources reconfiguration in runtime will be available. The monitoring system will be finished and the data will be shown using graphical dashboards.